I'm writing a book called Deep Learning. And there are already a couple of chapters, draft chapters that you can look at that cover some of the material I'm talking about. And you're welcome to upload and give comments. Download, I mean. Okay, so we've talked about neural nets, classical neural nets. One thing that has helped these deep neural nets is called dropout. Basically, it's injecting noise. It's 2012, as you've seen. And it has helped in a number of data sets listed below here. In particular, for this breakthrough network that Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton put out in 2012 that reduced the error rate, the state-of-the-art error rate on the ImageNet benchmark for image classification by a big amount, from something like 26 to 16%, and now it's down to 11, I think. And so, one of the ingredients was this regularizer. What is this regularizer? Very simple. While you're training your neural net, you put in some noise by flipping the outputs by setting the outputs of the neural nets to 0, the outputs of the hidden units to 0. So for each hidden unit, you're flipping a bit, a random bit, and if it comes out 0, you turn off that unit. And then at test time, you multiply all the weights by 0.5, just so that the expected value remains the same. So if you use a probability of flipping that's not 0.5, then you should adjust this accordingly, so that the expected value remains the same. So it's a very, very simple recipe. We used a similar recipe earlier for the inputs of a neural net in denoising auto-encoders, which I will talk about later, maybe tomorrow morning. But basically, you use this at all the layers, including the inputs, and it helps a lot. So let's try to understand a little bit why. There's been a number of hypotheses to try to explain why it helps. But the one that seems to survive all the tests is that it's a very particular form of bagging. So bagging is an old idea from the early 90s of machine learning, where you could improve a learning algorithm by training randomized versions of the algorithm, for example, by changing a little bit the data or the way the algorithm works, and just making the different learned predictors vote by some linear averaging. And so what happens here is, it's like if you have a family of neural nets corresponding to all the ways in which a different subset of hidden unit is used. So say this neural net is the one corresponding to only when the red ones are activated, the other ones are ignored. They're considered to be 0. And so you can see there's an exponential number of these guys. And each time you train with a dropout, it's like if you select one of them, you train for it, and because they all share the same weights, because there are different subsets of the same sets of weights, you don't actually need to train all of them to give examples to all of them. In fact, you won't, because there are many more of these guys than the number of examples. But because they share weights, you can then meaningfully take the average of all of them. Now, taking the average of all of them is not tractable in general, but actually it is tractable for the last layer, and that's what the divide by 2 trick does. And for the other layers, it's an approximation to the correct thing. But we've done experiments suggesting that it's a pretty good approximation. All right, so it's just a regularizer, but it's a different kind of regularizer. It's not one that corresponds to bringing the weights to 0. And it's funny because you're, making something more noisy, and somehow it's helping you. All right, I'm going to tell you about convolutional networks. I have already told you about a little bit about recurrent networks that are really important for temporal and spatial inputs. And they basically combine two, three ideas: local connectivity, sharing weights, and pooling. So local connectivity will reuse the same parameters for units that look at different portions of time or space. We'll share weights across time and space. And we'll use pooling to achieve some kind of invariance. So let's go through each of these. So a convolution between two sequences here, x and w, is obtained by this operation. And in sort of a neural net language, you can do the same thing by having the w be the weights and being shared in the sense that, say, this unit and this unit have the same input weights. So for example, the connection from this to this is the same, the connection weight from here to here or here to here is the same for all of those guys. If it was not shared, then each of the connections between any units would have its own, would be different. It would have its own, it would be a different degree of freedom. But if it's shared, then at every position we use the same weights. And it's shared and sparse, meaning that this guy only sees a subset of the inputs. And because it's shared and sparse, we can extend the input. Right? So if I've trained a particular set of weights W, I can apply it to a sequence X of a particular length or a sequence X of another length. I'm just going to get a sequence S of a different length. So if I apply to a longer sequence, I'm going to get a longer sequence in output. So this is unlike the usual neural nets, which take a fixed size vector and outputs a fixed size vector. Here, if I were to add an extra unit before here, I would just get an extra output as well. Is this clear for everybody? Okay. So that's the convolution part. It has sparsity and sparse connections and shared weights. The pooling part is that we're going to have layers that don't do a convolution, that do pooling. And the pooling is just, for example, the most successful pooling currently is called the max pooling. And what it does is each unit here just outputs the max of the units that it sees in its pool, that's its inputs. So here the max of 0.11 and 0.2 is 1, so it outputs a 1. And this one takes the max of these three, and it's still 1. Now you can see what happens if we take the input and we translate it to the right here by 1. We get this to be translated as well. And if we subsample, so if we only look at these over once every 2 positions, this is what we are doing here, then we get the same 1 here, whether the max is here, here, or here. So it's going to be invariant to a local translation, assuming this axis represents time or space. Actually, you can do pooling over time, space, or over features. So in other words, let me show you the next picture. So actually, we're going to do a bunch of different convolutions. It's not just one convolution. We're going to have, at each layer, we're going to have, think of it like different images, each correspond to a different feature computed at different locations. So for example, here we have 4 features. We call them 4 feature maps because for each feature we have the value of the feature at every position. So maybe you can think of a feature like an edge detector for a particular angle. And then the features of the next layer will have weights for performing the convolution for each of the feature maps at the previous layer. So it's like we're actually doing a bunch of convolutions, one for each of the feature maps here. Actually, for each pair of feature, one on that side and one on that side, we're going to do a convolution. And then we're going to add them up. So basically, what it means is each unit here is connected to all the units at one location. So this is this cube here. All the units at one location across all of the 4 feature maps that it sees as input. And this guy looks at all of the features in some neighborhood across all of the planes in input of that next layer. And when we're going to do the pooling, we could do it in space. So we can have, imagine a pooling unit which takes the max over only the same feature at different location, or it could be across features, so same location, different features. And this would allow to learn invariances that are not the translation, but other kinds of invariances that the system is trying to discover that would be captured by variation across those features. All right. So now we're going to move on to unsupervised procedures. We've talked about the good old neural nets. Now let me tell you about unsupervised learning, and motivated by talking about these challenges that we won in 2011 at ICML and NIPS. So these were transfer learning competitions where essentially you were given training classes and you're supposed to learn representations using these. And then on the test set, there would be new classes, but you wouldn't see the labels of these. You would have to compute a representation on those new classes, and then a very simple linear classifier would be applied to that representation, trained on the very few labels per class. And what the pictures show is how things get better as you consider deeper, more abstract representations. So here we applied the linear classifier on the raw data. Here we applied the linear classifier on the first layer, second layer, and so on. And each of these curves is accuracy versus log of the number of labeled examples, so per class. So this is 0, that means 1 labeled examples per class. That's 2, 4, 8, 16, 32. So that's not a lot of labeled examples, and you'd like those curves to rise as sharply as possible. And you can see that as you represent your data higher up, better somehow, it generalizes from fewer examples much faster. That's why we like these unsupervised representation learning methods, that they somehow discover representations from which you can learn from very little data. That's what these graphs illustrate. So principal components analysis is something I assume you've heard about, but what I'm going to tell you is it corresponds to a linear autoencoder. In other words, you can think of PCA as taking your input, doing a linear transformation into some representation, which you can think of a code or latent features, and then there's another linear transformation which happens to be the transpose of the first one, which gives you a so-called reconstruction. So it tries to be close to this. And if you have a bigger representation, it will be better. It will be closer. And geometrically, what is going on is it's considered a 2D case. So the input is in 2D, and these are the crosses, or the red crosses are the data. And let's say the code is one-dimensional. So really, we're only allowed to use one number to represent 2 numbers. So if the data is kind of a line like this near a one-dimensional manifold, a straight line, then the one number that summarizes them best is their projection on this line. So this is really the 1D representation of the 2D thing that minimizes the reconstruction error. So this is an example of a very simple autoencoder that's linear with squared error reconstruction. You can also interpret it as a probabilistic model that looks at the data as a Gaussian distribution with a particular covariance matrix that has structure, and where we only try to capture the leading eigenvector of the covariance matrix. There are a bunch of models, including PCA, which you can interpret from a probabilistic point of view as saying that the joint distribution between the input and some latent factor that explains the data is decomposed as a prior distribution on the factors times a likelihood or conditional distribution of the data given the factor. So in many of these models, the so-called factor models or directed factor models, the P of H, the prior, is factorized, meaning that we assume that each of the factors H1, H2, and so on are independent, at least on their marginal distribution. So P of H is P of H1 times P of H2, and so on. In PCA, those factors are Gaussian. In ICA, they're not. They're non-parametric. In sparse coding, we assume that P of H has a high probability of being 0 or near 0. So basically, those numbers are often 0. That's what we're assuming, or close to 0. And what it means is we're trying to think of an image like this A as a linear combination of pieces, and we're only going to be allowed to use a small number of pieces, say piece 1, piece 3, and piece 5. And each of these pieces is like a little image. And the H1 and so on are how much we're allowed to use of each piece. So we take a linear combination of these images, we get this image, right? There's a similar real example here, where the pieces are these edges that have been learned. It's called a dictionary. And now if we want to explain a patch of an image, we can find by an optimization method, which is an inference, find a good representation for this patch, which will be something like some proportion of this guy plus some proportion of this guy and some proportion of this guy. So the representation will be a bunch of zeros, 0.8 at the position corresponding to that guy, 0.3 corresponding to the position of that guy, and so on. Those that are active. So this is essentially what sparse coding does. It looks for sparse representation and looks for how to learn these weights that map those sparse representations to the input space with the smallest squared error. Okay, so PCA is nice and beautiful, but it produces a linear representation, and so we can't really stack linear representations. If we do, we just get another linear representation. So that's why Jeff Hinton was motivated to explore other models like the RBM that I'll be telling you about later. If you stack nonlinear representations where the mapping from X to H is nonlinear, then you get something out of doing this stacking, greedy learning of representation on top of representation. In fact, we showed how by using this pre-training of a deep supervised network using RBMs or sparse autoencoders, or denoising auto-encoders, I guess, in this experiment, we're able to get the error to be smaller, but this picture tells us more information. On the x-axis, we have the number of layers. On the y-axis, we get test classification error after having trained, fine-tuned, as we say, these deep supervised networks that were initialized using here randomly, and here using the unsupervised, layer-wise representation learning, either with denoising auto-encoders or RBMs. And not only the error is smaller, but whereas here we see as we add more layers, the thing that, the reason why people didn't use deep nets before was that, starting at 3 layers, it started to be worse, and then 4 was pretty bad, and 5 is off the scale. Whereas with this way of initializing, somehow we're able to train deeper nets. But even there, you see it started to be slightly worse at 5. So in this 2010 paper, we tried to understand whether, what was the effect? Was there some kind of regularization effect? Is it connected to optimization? It turns out that both effects matter. There really is a regularization effect, and that it's also connected to the optimization procedure. We still don't know, what is it that makes optimizing deep networks difficult, but there's some nice recent work starting to bring some interesting new light on this from Surya Ganguly at Stanford. But this is clearly still an open problem. One thing we noticed in those experiments that was kind of worrisome is that the early examples during training, if you have a lot of examples, imagine you have an infinite number of examples, a stream of examples. The first few examples you see, and here this is like 100,000 examples, no, 1 million example. Each of these blocks is 1 million example, I think, or something of that order. So it's a lot of examples. The early examples have more effect on the final function you find. So how much the function you get at the end depends on which particular example were selected is measured here on the y-axis. It's the variance of the final function with respect to variation in the data. By resampling the data, we get a different function, and we can measure that. And we see that the first few million examples have a much higher, especially the first few 100,000 examples, have a much higher impact on the final function than the later examples. Yeah. There is something related to this, which is something I call curriculum learning, which again has to do with the order in which we present examples. So this looks like a bad thing, but it could also be used to our advantage. It all comes out of the fact that we're not doing convex optimization. So the way in which we're presenting example, the order in which we're presenting them could make a difference. So the idea of curriculum learning is that by ordering or choosing examples properly, we can actually make a difference. We can get better results. We did an experiment in language modeling where we showed the learner easy sentences containing only frequent words, and then gradually show more difficult words, and it learned much better than if you show it just all the sentences in arbitrary order, even though it's seen less diversity of data initially. So it goes against a little bit of our usual thinking in machine learning. Yeah?
Oh, the comment you just made, is that because you speculate that your objective function could be submodular, or?
Because you get stuck during the optimization in what looks like local minima, and so the trajectory that you take in the space that you're exploring of the parameters matters, and depending where you start and how you orient this movement makes a difference. Actually, I have a picture later that maybe will help understand why I think this strategy is making a difference. So the intuition I had was that by starting with simpler examples, we're starting with a simpler learning problem. And then we're gradually making the problem more difficult. It looks like a trick that's used in global optimization technique called continuation or homotopy methods. And the idea is that we want to minimize some complicated objective function, but instead we're going to minimize something much easier, say convex. And once we found the solution to that, we're going to move it gradually towards the things that are more like what we want to optimize. So we have a family of objectives, and we're going to move along that dimension, tracking the local minimum along the way. That's what the continuation methods do. So you start with an easy problem, you solve it, and then you gradually transform the easy problem into the problem you care about, keeping track, staying close to the minimum local minimum as you move forward. And then the idea is you can see what would happen here. Even though this isn't the global optimum, in fact, it might be pretty bad, it's in the neighborhood of a good, almost a global minimum here. And by doing this, you actually approach the global minimum. So I'm going to recap the procedure for this unsupervised pre-training. We train some features using unsupervised learning, for example, to reconstruct the inputs by a backprop. Then we throw away the reconstruction weights, and we keep those features, and we're going to train more abstract features on top by using the same procedure again, and then we do it again. And at the end, we can do supervised fine-tuning. So I think I've made that clear. There is a variant of this which works surprisingly well, but can also overfit more easily, which is actually in the same paper where I introduced the other one, and it's called greedy layer-wise supervised training. And instead of doing unsupervised learning of those features, you can do supervised training. So the idea is you first train a supervised network, but I've sort of drawn it this way, where you reconstruct the Y here, you predict the Y given those features. But then you throw away those U1s, and you just keep the first layer. You train another MLP on top. Then you throw away these weights, and you can do it again and again as many times as you want. Okay. So one thing that happened, I think, kind of breakthrough happened in 2010. So until then, we had only these unsupervised pre-training procedures for training deep nets. We found that actually you could train a deep supervised feed-forward network simply if you played with the activation functions and the initialization. So we used rectifiers, and that was kind of the first time they were used in these deep supervised networks. There was an earlier paper by Jeff Hinton showing how you could use rectifiers inside RBMs, and we plugged them into deep nets, and it turned out with the right initialization that we were now able to train nets of, with depth 7 or something very successfully. And that was the start of a kind of a new era in deep learning. All right, so let me tell you a little bit more about RBMs. I've mentioned them several times. So they explicitly represent a joint distribution between inputs or visible X and latent or hidden H in a way that's very convenient. In particular, given X, you can predict H easily. You can sample H, you can compute the expected value of H, and vice versa. Given H, you can predict X or sample it very easily. And that's unlike most graphical models, where it's usually either easy one way and hard the other way, but rarely easy both ways. That's maybe why this was appealing. You can find a lot more details about RBMs and related models in this book that you can download from my website from 2009 called Learning Deep Architectures for AI. And also suggest this practical guide for training RBMs from Jeff Hinton in 2010. So RBMs are restricted Boltzmann machines. So what are Boltzmann machines? Boltzmann machines are probability distribution expressed through a so-called energy function. So we can, it's just a way to reparameterize P of X. The only constraint we introduce by doing this is that we're saying that P must be positive everywhere, right? So it's not a big constraint. It can still be close to 0. And so we now have a new parameterization which is written as some function of x, and in Bose machine, that function is a polynomial of order 2. That's it. It's a special case of something more general called undirected graphical models or Markov random fields, where we write p of x with an energy function that's a linear combination of functions of x called sufficient statistics. So here, the sufficient statistics would be x and x squared, basically, and all the combinations of xi, xj, and so on. So in the restricted Bose machine, we have a restriction, which is that there are no interaction between the x's and the h's. Whereas in the general Bose machine, any pair of variables, so here x could be both observed or visible, any of them. In RBMs, we make a distinction because we're going to decide that there are two groups of units, the x and the h, and there are no interactions between the h and no interactions between the x, only between an h and an x. And that's what this polynomial, this bilinear form tells us. So we get a bipartite graphical model. And because of this structure, you can see, if you know a little bit of graphical models, that given these guys, these are independent and vice versa, because there's no connection between them once we clamp these and vice versa. So that means we can do what's called block Gibbs sampling to generate from the model, the RBM. And the way block Gibbs sampling works is we start from some x's, which could be taken randomly, and then we're going to sample some h's given x. That means for each of these units, we're going to compute something fairly simple, the sigmoid of a dot product of x with some weights, and we're going to sample a bit, 1 or 0, according to that probability given by the sigmoid. We do it independently for each unit, and then we do the same thing here, but backwards, sampling each of those bits given those bits. And we can do it again and again, and each time we go up and down, we've done one step of a Monte Carlo Markov chain, which is called block Gibbs sampling. And one can show that this will asymptotically, as the chain goes to infinity, give you samples from the distribution captured by the model. So we have a reasonable way of sampling, which is more efficient than the traditional Gibbs sampling, which would only sample one variable at a time. So we have a model that has these nice properties, and we think we can sample from, but we'll see there are some issues with that. You can also turn the model into one that is discriminant by having some of the inputs, some of the visible be targets like labels, and some of the visible be inputs like an image. And once you've trained this, you can ask, like, what is p of y given x fairly easily. You can also train it in such a way that instead of just maximizing the likelihood of the joint of x and y, it maybe puts more weight on predicting y correctly given x. This is what we've done in this 2008 paper. You can also show that RBMs are universal approximators in the sense that if you have enough hidden units, you can represent any joint distribution on the inputs. It's still a shallow model, but like many other shallow models, it can represent any distribution if you give it enough capacity. But we'll use it as a stepping stone to build deeper things. I'm not going to go through this, but if it's easy to show, and it's instructive to go through the details of showing how the conditional p of h given x factorizes into the product of p of hi given x, which makes the whole thing easy to sample and compute expectations of, and so on. The other thing you can show easily by a little bit of algebra is, what is p of hi given x? And I said earlier it was a sigmoid of an affine of the input, the dot product of the input with some vector. And that comes out of the energy and just following the definition of conditional probability. So the definition of the energy for the RBM has this form b.x plus c.h plus h.wx. So it's a bunch of sums, and here it's a double sum. And the condition probability is just the joint, which is something like this, normalized, divided by the value of the joint when hi equals 1. So replace hi by 1, and when plus the case where hi equals 0. And then if you do the math, you end up with this. It's fairly simple. Since I'll put the slides online, you don't need to look at this carefully right now, but this is useful to get a fix on what's going on. So you can take any energy function and try to answer these questions, but it turns out for this energy function you get these nice answers, which depend, the specifics of the forms you get here depend on the fact that I've chosen 0 and 1 as values. For example, if instead of 0 and 1 you take minus 1 and 1, hey, magic, you get a tanh here. It's not really surprising either. Well, actually, it's not. No, sorry, I said something strong. You still get a sigmoid, but the expected value is going to be a tanh. Of course, probability is positive. So I've done this. Yeah, I think I'm going to skip all this math and go to some pictures. How do we train RBMs? So there are many methods, but most of them share this very simple intuition that I'm trying to illustrate here. We have some example x, and I'm calling it x plus here for some reason. And we have some energy function. So the x-axis here is x, it's the different configurations of the input, and the y-axis is the energy. The energy is the minus log probability normalized. So it's something that wants to be small at the data, that corresponds to a high probability for the data, and wants to be high elsewhere. So what training means is taking the current energy function and pushing it down where you have examples and pushing it up everywhere else. But actually, if you look at the math, it says push it up, especially in places where the energy is low. In fact, in proportion to the probability, which is e to the minus energy of these configurations. So the configurations that currently have low energy should be pushed up. But maybe you're going to say, well, that's weird. I mean, are we not going to unlearn the stuff that we're learning? Well, if you also have examples in this region, then the arrow going up and the arrow going down will cancel exactly, and then it will, stay there. But if somehow the model puts more probability in this region than the number of examples, justifies it, then this ball here will rise up, which is what we want, until there's an equilibrium between the forces pushing down on the energy and the forces pushing up on the energy. So in this picture, we have two kinds of examples, the data and these x minus, which is a sample from the model, also called generated or dream or fantasy samples or particles. And there are different ways we can generate these negative examples. The first algorithm that was proposed is called contrastive divergence, and it obtains this x minus by starting a Gibbs chain that I explained earlier at one of the examples, and then let the chain go for k steps, and that gives us an x minus. It turns out that it's a very turns out that even with CD1, so k equals 1, this works reasonably well. But in terms of the quality of the model, in terms of as a generative model, it doesn't work as well as the next thing that was proposed called PCD, or stochastic maximum likelihood, where instead of starting a new chain at each example to get these x minus, we just have on the side a chain continuously running that gives us the x minus whenever we want them. So each time we have a new example, we are going to say push the energy down for that example. We're going to take the next sample from the chain running in the background that gives us an x minus, and we push up on this one. That's it. It's a very simple algorithm. But it generally produces model with better likelihood than CD. In terms of feature learning, though, it's not clear that PCD works better than CD. In fact, sometimes CD might work better. And then there are some other versions that I'm not going to talk about, but these are the main ones. So if I recap what happens with contrastive divergence, we take an example from our data set. We start a Gibbs chain going up, sampling some H, going down, sampling some X, and so on. And then the last XH pair we've sampled, we're going to use to push the energy up at that location, and at the same time we're going to push the energy down. And the formula for doing that is pretty straightforward and was in one of the slides that I skipped, but it's not really important. And for PCD, it's similar, but we're just going to have our data, compute the H for it, use that for pushing down on the energy at location X plus, and then we have our chain, which we're going to update by 1 or k steps to give us a new X minus, and we're going to do the same thing with the reverse sign for that example. Okay, so that's nice, but something bad happens. And to understand what's going on, I need to explain a little bit about MCMC. Hopefully, you'll hear more about it in the next few days. So what the picture is illustrating is, well, the big picture is that things get worse as training progresses. And it becomes harder to train as your model gets better. Let's see why. So let's consider what's going on at the beginning of training. So this picture represents the density learned by the model. So the x-axis is the data, the x space, and the y-axis is probability. So initially the model is very flat. It says, I don't know anything, I'm giving equal probability to everything. And then as it sees more data, it starts to shape these bumps of probability. And as it gets better and better, it becomes sharper and sharper. That's what we want at the end of the day, especially if we believe this manifold hypothesis that we talked about at the beginning, that the right model should have very high probability in some places and tiny almost everywhere else. So we should have these really sharp peaks in probability. Now let's see what happens. We need to run these Markov chains to get our gradient for learning RBMs or Boltzmann machines in general. And we've seen examples of these Markov chains with Gibbs chain. They make a small move, typically to something not too far from where you started. And there are good reasons for this. And they want to make a move. So basically, a Markov chain typically makes a move to a nearby configuration that's probable. Well, it has to go to a probable configuration because that's what it's trying to do. It's trying to move along probable configuration so that the samples you get are all probable in the sense that they should come about with exactly the probability that the model assigns them. So the rare configurations should come rarely, and the probable configuration should come more often. That means most of the time you should get probable things coming out of it, right? So it doesn't want to go to unlikely places. It doesn't want to go to places of low probability. But if we have these manifolds that are separated by regions of low probability, the Markov chain will, hop, left and right here, and will never jump between these because it can't. It makes these small local moves, and it would have to go through these places that are unlikely, that are of low probability, and it's not going to do that. Or it's going to do it with a very small probability. And the sharper the model gets, the more this problem, becomes more serious. So there's a kind of vicious circle between the training, which makes the model sharper, and the mixing between modes, which becomes harder as the model gets better. But then if the samples we get are not representative because it visits this mode but not that one, then our training gets bad, and so it stalls. So I think that's one of the issues with RBMs, which we haven't completely fixed, but I'll tell you about some things later. that may help. One of the variants of, so there have been a lot of different variants of RBMs. The original ones are so-called binary RBMs. So both the hidden and the visible units are just bits, binary units, binomial units. But you can easily introduce continuous valued variables there in many ways. For example, from the exponential family. That's Maxwell in 2004. And for images, in particular, you really want to model the gray levels. You don't want bits. I mean, that works for MNISTs, which are black and white digits, essentially. But for real valued images, you want your model to really capture that. And so there's been a number of proposals over the year. The one that we found to work best is so-called spike and slab RBM. And I'm going to show you some samples from it when it was trained with CFAR images, which are 32 by 32 little images of objects, just like you find from Google image search. So the training data are like this. And the things that it generates are like this. And we've paired them here. So for each generated example, we've found the training example that was closest, just to make sure that it wasn't just copying something from the training set. And you can see that it doesn't really, it's not just memorizing training examples, it's actually generating new images that don't actually look like real objects, but if you squint a little bit, it's pretty artistic, and they have like an object-like nature to them. So in terms of parametric model of images, this is kind of, that can generate images. This is kind of the state of the art. And we'd like to do better than that. We want to do better than that, but there are some obstacles I'll tell you about later. Okay, and actually, you can also view this as a motivation for a totally different way of doing unsupervised learning, and it's all the variants of auto-encoders. So this is what I'm going to tell you about probably for the rest of the lecture today. Well, the rest of the lecture, there's 10 minutes left, is that it? No. 40 minutes left, right? Okay. So that should be fine. So instead of talking about the graphical models we've seen up to now, we're going to be talking about computational graphs. So the thing we're going to be manipulating is not the graph where the nodes correspond to random variables. The thing we're going to be talking about are different kind of graphs which do the computation we want. So that's what we have in a regular neural net, like we talked about at the beginning today. And we're going to get a family of these graphs potentially by sharing parameters. For example, in recurrent nets and graphical models, we can get a family of graphs by sharing parameters in various ways. Okay, so we'll see how we can construct probabilistic models using these kind of formalism, which is different. So I've already introduced simple autoencoders through PCA, and you can make them nonlinear by simply inserting a nonlinearity like the hyperbolic tangent or the sigmoid at the output of the encoder and the decoder. And you can minimize a reconstruction loss, the simplest of which is a squared error, but nowadays we prefer to think about it as a negative log probability under some distribution here, which would be Gaussian, but if you have bits, then you might want to use binomial log probabilities or Bernoulli log probabilities. Oh, another thing, the traditional autoencoders from, as they were proposed in the late 80s, or like you find in PCA, they have a so-called bottleneck. So the representation here is smaller than the input representation. And it's because we have a bottleneck that it does something useful. And that's one way to regularize an autoencoder to prevent it from learning the identity, right? If we're just going to reconstruct the input, why would it not learn something trivial that's useless? Just copy the input. Well, you need to regularize somehow, And constraining the dimension to be less than the input is the old way of doing it. As you'll see in modern ways, we find better results by allowing this to be bigger, so it can have more capacity, but still regularizing in different ways. So this slide kind of then summarizes a lot of the things that we now understand about autoencoders. So autoencoders take the input and map it to a representation. From that representation, we're trying to predict the input again and put a high probability on it. Or if you want, in the simplest sense, just minimize some kind of reconstruction, squared reconstruction error. So what we're trying to do is to make this reconstruction loss, whatever it is, small at the training examples. And we don't care about the rest, but just by the fact that we're regularizing, it can't make it small everywhere. So it's going to try to make it small at the training examples, and necessarily it's going to have to be high elsewhere. The regularization is going to prevent it from making it small everywhere. The other thing we've learned is that if you take this reconstruction vector, in the case of squared error, you subtract the input, this vector points in the direction of increasing probability. So I'll have a picture to illustrate that, and hopefully it will become clear. And we can prove that. And you can also take your autoencoders and actually construct a generative model out of them using a Markov chain that's associated to the autoencoder, which encodes, decodes, and add noise, encodes, decodes, and add noise. So I'll explain all these things in the next few slides. First of all, you can use autoencoders just like you were using RBMs to train deeper autoencoders or pre-train supervised networks, and that works well, very well. The loss, as I said, doesn't have to be squared error. It could be, for example, cross entropy, which is just a Bernoulli minus log probability. This is a multinomial loss. In general, you take your variables and construct a parametric model, make those parameters a function of the output of the network. The denoising autoencoder is probably the one that's best understood, so I'm going to spend time on it. The way the denoising autoencoder works is slightly different from a regular autoencoder, and the difference is that instead of giving the raw input to the encoder, we give it a corrupted input. So we take the input, we stochastically corrupt it, like setting some inputs to 0, like in dropout, or we can add some Gaussian noise, things like that, that are very dumb, and kind of allow the space of these guys to be much larger than the space of these guys. And the rest is the same, but now it has a harder job because it wants to reconstruct the clean input. So we compared reconstruction with the clean input, and we want the KL divergence or whatever, the loss here, to be small. So it needs to undo the work of this random corruption. And if you think about it a little bit, you'll find that this denoising job is hard unless you know the right distribution. I'm going to show a picture that makes it clearer. So imagine the data lies near this one-dimensional manifold, or this, in general, this low-dimensional manifold. And now we corrupt it by adding Gaussian noise. That's easier to visualize here. So what happens is that the points get mapped to a region that's around the manifold, but it's away from it typically. In the high dimension, take a random, you have got a low-dimensional manifold and make a random move around it. That's typically going to move you away from the manifold. Okay, so we've got these corrupted inputs, and we learn a function that maps a corrupted input back to the manifold, back to the clean version. And so what we're learning are these arrows. We're learning a function that maps from a point outside of the manifold towards the manifold. That's what the denoising autoencoder is doing. And if it can do that, it can learn where probability is concentrated. It's where it points. So that's why I'm saying this arrow, reconstruction minus input, points towards the direction of increasing probability, the so-called score, d log p dx. There's also some connection between denoising auto-encoder training and something called score matching, which is another inductive principle for probabilistic models. And you can show that some autoencoders correspond to performing a form of score matching. If we compare to RBMs, that there are some advantages that we don't need to run a Markov chain in order to train them. There's something I didn't have time to mention. That the reason we're running this Markov chain for RBMs is that we want to get the gradient of the so-called normalizing constant or partition function, which is intractable. Here we don't have such things. And we can measure the thing that we're optimizing, which is the reconstruction error. So that's nice. Let's see what's the kind of geometric intuition behind these autoencoders, these regularized autoencoders. So let's consider your training data as points. And let's say there is some structure, like a manifold, near which they pass. And we're going to train an autoencoder so it's going to learn to encode into some representation in such a way that it can decode back into nearly the same place. At the same time, there's some kind of regularization, maybe due to this noise that we're adding, or other form of regularization like the sparsity, that makes the representation want to be essentially insensitive to the input, to not vary with the input. So in the case of sparsity, we want the hidden units to be all zero. That's what the regularizer wants. In the case of the denoising, something similar is actually happening, and it takes a little bit of math, but you can show that it also wants the representation to be insensitive to the inputs. Okay, so what happens is if we take an example, the learner has to find representations that will be sensitive to changes along the manifold, because going from here to here, I get another example, and I want a representation for this guy to be different from the representation from that guy. Otherwise, when I reconstruct, I would not be able to distinguish them. So the representation has to vary as I move in this direction. On the other hand, for this direction, I don't care. The representation can be invariant. If I move in this direction, it stays the same. And I'm not going to lose anything in terms of reconstruction error. So that's what it does. It throws it away. It's just like PCA. We throw away some direction, and we keep the directions that matter most, which are where the data varies. But instead of being assuming that the variations is only along one hyperplane, here we're only making that assumption locally. And globally, it could be any shape. So we can now learn manifolds that are not just flat, but can be curved. And actually, you can try it out. And so for this 2D toy data, you can see these arrows representing those vectors of reconstruction minus input, telling you in which direction the reconstruction wants to go. If you feed it an input here, it wants to go in this direction, and so on. And notice here is a kind of special point where it doesn't want to move because it doesn't know in which direction to go. And there has to be such points, like along that line here as well. So this gives us a kind of geometric understanding of what is going on. It's learning a vector field that estimates a gradient field. So the gradient field is the derivative of the log density. So the difference between a vector field and a gradient field is that a gradient field is a vector field where each arrow corresponds to the derivative of something, some function. So the way you can now turn this into a sampling method essentially is to say, okay, so let's zoom in on our manifold and have a piece here, and maybe there's another piece here. We're going to have a Markov chain that is going to start from an example, corrupt it, and then we're going to sample from the reconstruction distribution corresponding to what has been learned by the encoder-decoder pair. So this pink thing is like a Gaussian that says, well, if I observe this corruption, the clean one could have been anywhere within this region. This is my uncertain distribution about what x should be. So what I'm going to do is sample an x from there. And then I'm going to do it again and again, and this is going to walk along that manifold and actually produce samples from the distribution. So I'll come back to this, but we've shown that if you follow this very simple recipe, corrupt, encode, decode, sample from the reconstruction distribution, and do it again and again, you sample from a distribution that the model has estimated, and that's an estimator of the data generating distribution. And it works in practice. I'm going to skip a few things here. Well, actually, maybe these pictures could be interesting. So one thing we've learned by thinking about this geometrically is these representations that we learn, if we look at their derivatives with respect to the input, that tells us what kind of variation in input our representation is sensitive to. If we come back to this thing, this arrow here is the direction to which my representation is sensitive to, and it happens to be a tangent to the manifold. So when you train an autoencoder, you're essentially implicitly learning the structure of those manifolds near which the distribution concentrates, and you can recover those tangent vectors. In high dimension, they will form a basis for the tangent plane by looking at the derivatives of the representation with respect to the input. So derivative is, how much does h, the representation, change with respect to x, the input. That's a matrix, and that matrix has singular vectors and singular values. And when a singular value is large, that means the corresponding singular vector corresponds to a direction where, like this, where a small change in input means a large change in representation. And when the singular value is small, so when the singular value is small, like would be in this direction, that means the representation is throwing away that variation. So we can actually visualize those singular vectors. So for example, for an autoencoder trained on MNIST, you can look at the leading singular vectors of the derivative dh dx, the Jacobian, and they make a lot of sense. What they mean is I could take this and add a little bit of any of these, actually any linear combination of them, and I would get something else that would stay on the manifold, and it works. These things are like saying, oh, move that 0 a little bit to the right or to the left, or move up or twist it. So you can play that game, and it works. And that's essentially why the sampling works as well. The sampling is going to move around by making these small moves. You can do it for other digits, and you see that the tangent vectors are very different from what you get for another image. So the manifold is highly curved. In one place, the tangents point in one direction, and in a slightly different place, well, here's a very different place, it's a totally different set of vectors. And of course, the kind of deformations you can do to a 2 by simple addition are very different from the kind of deformations you can do to a 0. If you try to do this with local PCA, which is just a mixture of PCAs, you get garbage. The reason you get garbage is because you don't get this kind of sharing that you have with distributed representation. It's like in each region, you have to learn your PCA, and you don't have enough data for it, so it doesn't generalize nearly as well. If you do it with an autoencoder, here it's called a contractive autoencoder, you you learn these tangent vectors, which again are meaningful, and they talk about taking some parts like the head and moving it, or the legs and moving them and stuff like that, which is typically what you would expect to see. Yeah, we've used this in a fairly successful algorithm called the manifold tangent classifier. So let's see the geometric picture here, because that's easy to understand. Imagine now, instead of having one manifold, we have a bunch of manifolds, one for each class. So of course, it's a simplified picture, but it helps. So here I drew, the class 1 manifold and the class 2 manifold. So h here represents your representation function, and dh dx, in directions where it's large, corresponds to the tangent plane of the manifold as it's been learned by your representation learning algorithm. And now, let's say you want to train a classifier that separates between class 1 and class 2. So I introduce a new function f, which would be something like, probability of class 1 given x. So we'd like that function to have the property that it's insensitive to movements on the manifold. So if I'm here and I move a little bit to the right, I would like f to be the same. Geometrically, that means that df dx and dh dx should be orthogonal. So in other words, if I make a small change in the direction of the manifold, I want no change in the output of the function. So if I move in this direction, the function should be the same. If I move orthogonal to the manifold, I'm quite free to change f, because I expect that when I move orthogonal to the manifold, I might approach the other manifold. In 2D, you have to, because there are only 2 dimensions here. But in general, there'll be some small subset of directions where you move on the manifold, some small subset of directions where you approach the other manifold, and the other directions don't care. So we've, in NIPS 2012, we had a paper that won an award by using this trick to regularize a classifier by asking it to have this property that its derivative with respect to the input would be orthogonal to those leading directions learned by an auto-encoder. All right. There is another variant of autoencoder that's interesting to talk about, that was introduced by Yann Lequin in 2008, and his collaborator, in particular his students Korai, Kavukoglu. And the idea is interesting. It's a kind of a mix between autoencoders and sparse coding. So imagine an autoencoder in which we introduce an auxiliary variable, so a free variable, which is going to be the code. Normally, in an autoencoder, we have the input passed through the encoder, and then that directly becomes the input of the decoder. But let's say we don't force the output of the encoder to be the same as the input of the decoder. But we ask them to be close to each other, but not necessarily the same. So now we have some degree of freedom here. We introduce this extra variable z. Previously, z was fixed to be a function of x. Now, z is like non-parametric. For each example, I've got a representation z that's free. So I've introduced something non-parametric in this thing. And I'm going to learn both the z and the parameters of the encoder and the decoder. And now the connection with sparse coding is I'm also going to ask z to be sparse, so to minimize, say, the L1 norm of z, the sum of the absolute values of z. And of course, I'm going to minimize reconstruction error, meaning I want a reconstruction here, x tilde, to be close to x, so minimize the squared error here between these guys. So we've got these 3 terms. We want the reconstruction error to be small. We want the predicted code to be close to the free code. We want the free code to be sparse. And if you add these things together and you optimize, you get something that actually works. And it works similarly to sparse coding, but it's comes with a big advantage, actually a couple of big advantages. One of them is that now we have a way to approximate finding Z by just running the encoder. In fact, the way it has been used is once we've trained this and we want to use it for a classification, we just throw away the decoder, which is kind of the generative part, and we just keep the encoder as a pre-processing for the next layer. And this has been used in a bunch of computer vision applications because that's what Yann LeCun does. And you can introduce extra constraints like that nearby codes in space corresponding to different patches would somehow turn off and turn on together by generalizing the L1 penalty to an L1-2 penalty, which is a square root of a sum of squares. And then you get these nice patterns. So these are the filters, the preferred inputs of different units, which are now organized according to a topology. Because of this penalty, there's a neighborhood between units. They're not in some arbitrary order. And you see that nearby units compute similar things, which is and you get these patterns that you also find in the visual cortex. All right. So now we've talked about these single layer learners, and they can be combined in various ways to build deeper nets. I've already introduced some simple ways, but there are other ways. What are reasons why these single layer learners are interesting? We've seen that we can initialize deeper nets with them. We can initialize, as we'll see, deep auto-encoders, deep Boltzmann machines, deep supervised networks. And we find very often, but not always, that by doing this initialization, we get better training and test error. So this seems to be some optimization issue that I've mentioned previously. So why would that be the case? If you imagine that training a deep architecture is hard from an optimization point of view, and training a shallow one is easy, then if we can get something reasonable for initializing a deep one by optimizing each piece separately, then that's a reasonable thing to do. There is an interesting result from last year that if you try to train a deep supervised net, and we have some examples of tasks where every machine learning methods we've tried fails. But if we break the problem into two parts, and we basically have two networks, one for the first level and another network for the second level, and we tell the first network some hints about what it should be doing, then suddenly training the big thing becomes very easy. So really it's another example of, well, initialization matters, but here we use some prior knowledge about the decomposition of the problem into subproblems. And if we pre-train by this prior knowledge, things that were unlearnable apparently becomes learnable. So that's this iClear 2013 paper. Okay, so let's go quickly to some of the ways we can combine RBMs and autoencoders. So we've seen already that we can train an RBM, another one, or an autoencoder, another one, and just take these weights as initialization for a deep supervised network, and then add these extra free parameters and tune the whole thing together. That was the 2006 thing. Same year, Ruslan Salakutinov and Jeff Hinton showed you can do this for deep autoencoders. So what is a deep autoencoder? We've trained, say, 3 autoencoders on top of each other. Well, we have a deep autoencoder, which is encoder of the first one, encoder of the second one, encoder of the third one, and then decoder of the third one, decoder of the second one, decoder of the first one. So basically you go up, 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 down, down, down. When you go up, you use the encoders. When you go down, you use the decoders. So that's a deep autoencoder. And they've shown experiments where it learned pretty compact codes. This kind of thing has also been used for what's called semantic hashing, where the codes are in the middle are small and binary, and that's useful for information retrieval. You can also stack RBMs and autoencoders into something called, which you could call a deep recurrent autoencoder, where what happens, so I'm going to, for the first layer, I'm going to use the initialize with the weights of the first autoencoder or the first RBM, and same thing for the second and third. And the way I'm going to compute, in general, this is time here, but not time of a time series, but time of evolution of the system, or think of a Markov chain or something like that. So at any time, each layer is going to be updated by looking at the layer above and below, and doing the sum of the dot products corresponding to these inputs coming into this one, and then sending the result to the layer above and below the next time step. This creates a kind of graph like this, which is the kind of computation which you can think of as a big recurrent net with a special architecture. And it's the same architecture actually that you find in the Boltzmann machine, which is here, where instead of sending deterministic quantities, you send bits that have been flipped according to the sigmoidal probabilities corresponding to each hidden unit. But it's the same architecture. There are some tricks to initialize those weights, because initially in the chain here, you see the units here only take input from below, but eventually they take input from both below and above. So one trick is that when they take input from below and above, you have the weights so that the activations coming in here aren't twice as large suddenly. And the same thing for the Boltzmann machine. So you start with the full weights, and then you halve them appropriately when the inputs come from above and below. Then there is something I haven't talked about yet, which is the deep belief net, which I think is the name deep belief net has been wrongly used often as meaning deep learning in general, but really what it means is a specific probabilistic model that has the following structure. We have the visible or input units X, and let's say we have 3 layers. We're going to decompose a joint between all these guys as a product like this, where we first going to generate the top level units with an RBM. So we know how to train an RBM between 2 layers. Then given H2 here, so we can sample from these guys, say by Gibbs sampling, going up, down in this RBM. We have an RBM between H2 and H3, so we can sample from it like this. And then given H2, we're going to sample H1 using the weights of the second level RBM here. And then given H1, we can sample X given the first level RBM. So all of the lower level RBMs, we only use the downgoing weights, the downgoing conditional distribution, to generate the lower layer given the upper layer. And only for the top level layer, we do this Gibbs chain. So we sample at the high level, and we run this Markov chain in the more abstract space. And then we project it down in, say, the pixel space. The thing with the deep belief net is that it's not clear how to train it. So the way that has been proposed for training it is first to just train these RBMs and stack them, and then to use an algorithm called the wake-sleep algorithm, which was proposed in the 90s, but it doesn't have a very clean justification and hasn't been used much since then. As we'll see tomorrow, actually, if we have time, there's now a flurry of recent papers looking back at this algorithm and some modern variants of it. Okay. you can do the same kind of thing as the DBN for autoencoders. So you can train a stack of autoencoders, and then when you sample, you can run these Markov chains I said can be defined for an autoencoder, in which you encode, decode, sample from some distribution, corrupt, and do it again, sample from the distribution, corrupt, basically add noise, and encode, decode, and so on. And then you can just apply the decoder of the lower layer and the decoder of the lower layer, and you project back in input space. So it's exactly analogous to the DBN. And then there is something I invented last year, which generalizes the denoising autoencoders in a different way, called generative stochastic networks. And I guess I'll tell you more about it tomorrow, but the architecture is similar to what I've shown before, where layers take input from layers above and below and send their outputs to layers above and below, but now there's noise injected everywhere, just like in a deep Boltzmann machine. And the difference is it's trained differently. It's trained with, for example, reconstruction error. The fundamental difference is that we're seeing this as learning a Markov chain that's basically the machine that generates examples. So in all the things we've seen with Boltzmann machines, we have a distribution P of x that's parameterized by some formula. We've seen, for example, this polynomial, e to some polynomial. And then we devise a procedure for sampling from it. Here what we're doing instead is we're directly parameterizing the procedure that generates samples. So this thing is just a machine that spews out samples, and it has parameters. And it turns out that there are ways to define a training criterion for such machines, such that it generates samples with the right distribution. It's trying to make the chain generate samples with the right distribution. So it's a different way of thinking about training probabilistic models. I guess I'll get back to it tomorrow. So the simple denoising autoencoder is a special case of this, where we take an input, we corrupt it according to some fixed corruption distribution, and then we have our autoencoder, which does a denoising that has a model of the probability of a clean input given a corrupted input. So we sample a clean input given a corrupted input, and then we corrupt it, and then again denoise it stochastically, sample from the denoising distribution, and do it again. And that's the Markov chain. So there were some previous work that I mentioned about the denoising autoencoder showing that the difference between the reconstruction and the input, these little arrows that I showed in the vector field, estimate d log pdx, called the score. And that's the direction, this thing is the direction in which p of x wants to increase the most. But this was the first probabilistic interpretation of denoising autoencoders. But the problem with it is it's rather limited. Actually, there was a first one with Vincent's work with score matching, but it required a particular parameterization. This one works for any continuous inputs, so it doesn't tell anything about discrete inputs. In fact, derivative of the probability with respect to the input, that doesn't make sense if x is discrete. And it works for Gaussian corruption and a very strong assumption about the noise being small and square reconstruction error. So fortunately, last year we've been able to generalize this to any kind of denoising autoencoder, to any kind of reconstruction distribution. The input could be discrete, could be continuous, whatever, it doesn't matter. The proof is much more general. And what the math tells us is that as we make our denoising autoencoder better in the sense that it approaches the true denoising distribution, in other words, the conditional distribution of the clean data given the corrupted data, then the stationary distribution of the Markov chain that is generated, as I explained, by going, corrupt denoise, corrupt denoise, corrupt denoise, approaches the data generating distribution. So that's the statement I was talking about earlier. All right, there are only a few minutes left, and I'm sure you're all tired, but maybe before we stop, I'd like to entertain your questions. Yes?
How do you train the denoising auto-encoder if you have no unnoisy training data?
Oh, that's very easy. Okay, so there's a misunderstanding here which comes from the name denoising. You're trying to capture a distribution. You're not actually trying to do denoising. You're trying to capture a distribution. So you have to have examples of that distribution. You've got some x's that come from some distribution, and you're trying to estimate p of x, but in an implicit way through this Markov chain. So you're not actually trying to do denoising. In the classical denoising, you would have, for example, I have speech that's being corrupted because of noise in the microphone in the room and so on. And so the way you would learn to denoise here could be that I have the clean speech with a microphone near to me, and I have the noisy speech recorded on my phone or in my car. And then I would learn to map one to the other. That's not what we're doing here. We're taking whatever data you have, and we're trying to learn its distribution. And the way we're doing it is by adding some arbitrary noise, like Gaussian noise, or this masking noise, which is setting some bits to 0 randomly. And the purpose of this noise actually is to go away from the manifold. So, and this is actually something we discovered. It wasn't obvious initially. Well, after the fact, it's obvious, but one question, I guess the better picture is this one. One question is whether the kind of noise we use in the denoising autoencoder should be like a random translation, like moving on the manifold, or should be like Gaussian noise, which has nothing to do with the distribution in the manifold. And some people in my lab were saying, oh, we should use noise that corresponds to the kinds of variations we see in the data. And other people were saying, no, we should use noise that's unrelated to the data. And it's the second theory which is true. And now we understand better the math and so on, and it makes a lot of sense because we want to move away from the manifold so that what it learns is to point towards the manifold. And if you take you add something random, it will typically move you away from the manifold in high dimension. Yes?
So you presented like a really broad picture of all the architectures that are available.
Yes.
In your opinion, at the current moment, is there an architecture that has the best theoretical or empirical basis available to
I wish. Well, so the Boltzmann machine family has a nice theoretical basis, but we also understand better its limitations now. At least we know there are obstacles that we currently don't know how to fix. We've tried things like tempering, for example. I'll talk about that tomorrow. The sort of deep supervised conv nets are, beating everybody else on object recognition, and the math is really simple, and we kind of understand what they do, but they're limited in what they can do. They can't do things like question answering or fill in missing values or the kinds of things that generative models can do, like, say, speech synthesis or machine translation, where the output space is rich. So they're very powerful, but they're limited. And we'd like to have the best of both worlds, right? We have something that can be trained easily, that can do more than just do simple classification. And we have a bunch of unsupervised learning methods, none of which currently is, has reached the same level of maturity than those deep nets that win those competitions. So that's where I'm going. That's, So I think the denoising autoencoder is something that was working well, but that we didn't understand. And now we understand it better and maybe opens the door to different kinds of generative models. But I think there should be a lot more exploration in the space of these generative models and supervised representation learning. Yeah.
You had already mentioned that connection between infinite neural networks with and Gaussian pulses.
Yes. Yes.
Is there a similar thing with logical pulses? Or infinite?
I don't know. Both machines with an infinite number of hidden units. Well, we can show that both machines with an infinite number of units can learn anything. I mean, they don't need infinite, they just need 2 to the n, where n is the number of inputs. Yeah, I don't know.
That's a good question.
Yes?
So there's a tendency that in auto-encoder and deep learning we try to make our hidden neurons as ineffective as possible. So in dropout training we just tell the network be invariant to removing of neurons, so prevents them to being too specialized. And convolutional nets, which as you said, everything right now in image processing are also like use the same weights over and over again. Is this a general pattern?
There's a general pattern that regularization is an important concept in machine learning, yes?
Yeah, but this type of regularization, this type of regularization, which actually...
Well, so there's something, I guess there's a connection with Gaussian processes here, which is one of the lessons of many things we've seen in machine learning is it's usually better to have a bigger model, even infinite in the case of Gaussian processes, that's well regularized than to have a smaller model. And so we see this with dropout, where we have bigger nets, really big nets with 100 million parameters, but that are regularized in a smart way. Somehow that combination works better and generalizes better and is able to represent more complex things at the same time. All right, thank you very much and see you tomorrow.